Hello, my name is Sirawit Harnchariyakul. I'll be presenting about problem number 5, ping pong rocket. The question is mentioned here, and the parameters are diameter of the container, 2, height drop and initial speed, 3, celluloid versus plastic ping pong balls, and 4, maximum height against percentage of water in a good container. So the setup contains the following and uses the tracker app to track the height of the ping pong ball. Comparing between celluloid versus plastic balls physically and the diameter of the container. The freefall model is F arrow over F body is equal to beta V squared, where beta is density of air times cross-sectional area times coefficient drag over 2 mass of ping pongs times gravity is reduced to minus G, parentheses 1 plus beta V squared is equal to dV over dt, where low A is greater than density of ping pong ball. When the container hits the ground, we can explain using Navier-Stokes, where vector field is more than 0 and divergence of fluid must be 0. We can find the forces being like here using this equation to explain it. Collision model, we can use the formula H file is equal to terminal velocity squared over 2g times natural logarithm, parentheses 1 plus v after impact squared over vt squared, where vt or terminal velocity is equal to 1 over root beta, which is around 8.94 meters per second, where beta is mentioned prior and coefficient drag is around 0.4 plus or minus 0.1. Assumptions and ideal conditions are here, and comparing between celluloid versus a plastic ball at the coefficient of friction, or mu, using the research paper we can find this graph. The maximum velocity of a meniscus at impact with the container moving can be expressed as u0. The function confinement factor lambda can be rescaled with the aspect ratio of h over r. And the initial speed and initial height test shows the result that increasing the maximum speed and initial speed and the drop height will increase the maximum height, although there seems to be a plateau due to the nature of natural logarithm equations at around 20 meters. And we can use the formula to change it to a curve. Use it is equal to y equals 4 natural log plus 1 plus x over 79.9. Celluloid versus plastic. A plastic ball has a greater friction, meaning at slower speeds it's more noticeable, but at higher speeds it's basically indistinguishable from another at greater heights or speeds. Impact of diameter size, we use the following diameters. Increasing the container's diameter will increase the maximum height, although it seems to be a saturation point, meaning a diminishing returns. The maximum height against the percentage of water. When the result indicates increasing amount of water will yield a better outcome until a certain point, meaning it's a parabolic graph. We find the optimization around 70% of the container. Answering the question, what is the maximum we got with up to 2 liters in water? So we got theoretically 4.4 meters, but actually we got 3.9 meters due to aerodynamic features and the surroundings of outside. Conclusion, when the ping pong ball and container hits the ground, the ping pong ball will be launch creating height. The speeds before and after rebound and initial height will increase the maximum height, although there's a threshold at a certain point. The higher friction coefficient will lead to less height, although at higher speeds it will be less noticeable or indistinguishable. Increasing the container's diameter, higher maximum height will be achieved until a saturation point, meaning diminishing returns, and increasing the amount of water leads to better outcomes until a certain point where it loses height at around 70%. Thank you.